So in section 8, let's continue on page 452. Bottom of page 452. Carbon chains also exist in a cyclic form with double bonds as shown in the following table. These are known as alkenes. Write the formulas indicating the number of carbon and hydrogen atoms in each structure. Then complete the last column in the table by writing an ordered pair to indicate the number of carbon atoms and hydrogen atoms in each structure. So please work on the table that you see on page 453, and then also number 11 right after the table. Okay, so the very first one, cyclopropene, I do not have on this table that you see here, but in that example, there's 3 carbons and there's 4 hydrogens. So that gives you the 0.34. What about the first one here, the cyclobutene? How many carbons are there? 4. So C4H, sorry? 6. So what's our point or the ordered pair? 4, 6. The next one, what do we have, Nicole?
C5H8.
So the point would be?
5A.
Next one, Alexis?
C6H10.
And the point?
610.
So that was easy enough. Now the next part gets a little trickier. They want you to come up with a formula, and you have to figure out how to go, for example, from the 6 to the 10. Any ideas?
Take C times 2 minus 2.
One more time?
Take C times 2 minus 2, so like 6 times 2 minus 2.
Oh, okay. So you think 6 times 2 minus 2. Let's see if that works. You'd have 12 minus 2, and that does equal 10. Let's try another one, see if it works. Let's move up one. Let's take 5 times 2 and then subtract 2. That will be 10 minus 2, which does equal 8. So in the first column on the bottom there, what should be after the H? Well, 2 is part of it. 2.
10 minus 2.
Yes. I wrote it kind of big. It's actually supposed to be a subscript. So then that also will go in for the point. The first value would be n, the second value would be 2n minus 2. So number 11, find a linear model that gives the number of hydrogen atoms for a given number of carbon atoms. When they say find a linear model, they mean to find the equation of the line. So we want the number of hydrogen atoms for a given number of carbon atoms. What should be on the right side of that equation? Any ideas?
Wouldn't it be the same thing?
Except we changed the variable. We're going to call it C now instead of N. We would take the number of carbon atoms times 2 and we would subtract 2. And there's our equation. Any questions on 10 or 11? Okay, the lesson wrap-up. What's the point? Sometimes a linear relationship is apparent from the description of the situation. When it is not, we can use a linear equation form y equals mx plus b and information about the situation to write the equation. What did you learn? How to write the equation of a line using a point and slope or 2 points, and how to model linear situations in context. How big is big? At what point should you use y equals mx plus b to find a linear model? We didn't do that on this one, although it is in that form. Y equals mx plus b. So when does it become helpful to do that, to use y equals mx plus b?
Always helpful.
It's always helpful? Okay, some people believe that, yes. Sometimes I think when the numbers get bigger and the slope maybe is difficult to work with, 2 is pretty easy to work with. And I kind of use guess and check and inductive reasoning. When does a problem become too big or messy for intuitive approaches? Again, when we're dealing with like the fractions and big numbers. So Section 8 homework has paper homework and my math lab. Section 9, hot and cold. We're on page 456, section 9. Use the table of temperatures to answer the questions that follow. So we have Celsius temperatures and we have Fahrenheit temperatures. Number 1, there is a linear relationship between Celsius degrees and Fahrenheit degrees. Find and interpret the values of M and B using the table provided. Be specific and use the temperature context provided. Okay, so from the table we should be able to find the slope and also the b's. Let's look at the slope first. Remember how to find the slope from a table? If we think about the slope formula, the slope is the change in y's over the change in x's. So look at the y values. How are they changing? How are the y values changing in the table? So we're talking about the Celsius temperature, the Fahrenheit temperature? Fahrenheit, okay. How are the Fahrenheit temperatures changing? Getting bigger. By how much? How'd they go from 32 to 41 and 41 to 50? And 9. Yeah, they kept adding 9. Since we're adding 9, it's a positive 9. Now, what's the difference in the Celsius temperatures or the x's? And those are increasing by 5. So again, it's positive. So there's our slope. So for every degree increase in Celsius temperature, so for every 5-degree increase in Celsius temperature, what happens?
There's a 9-degree increase in Fahrenheit temperature.
Exactly. There's a 9-degree increase in Fahrenheit temperatures. Okay, so what is B? from the table?
32.
32. If they asked us what the y-intercept was, then we'd have to say 0, 32. So what does the 32 represent?
Where crosses the y-axis, which is when Celsius is at 0 degrees Fahrenheit is 32.
Okay, so when it is 0 degrees Celsius, it is 32 degrees Fahrenheit. Any questions on number 1? Let's go to number 2. Make a graph of this data. Explain how the linear relationship is evident in the graph. Okay, so what will we have across the bottom?
Celsius.
Good, Celsius temperatures. So on the side then will be Fahrenheit. So if we start out at 0, what increments would you like for Celsius? Yeah, let's go with 5. How about Fahrenheit? We have to get up to nearly 70. Yeah, let's go by tens. Okay, so our first temperature is 0, 32. And 541. 1050. 1559. And 2068. And then we can draw the line. So we made our graph. Now it says explain how the linear relationship is evident in the graph.
Straight line.
Yeah, the points fall in a line. Let's go to number 3. Identify the values of M and B using the graph. Explain how you found these values from the graph. So the slope, how would you find that from the graph?
If it was like an actual graph of the world, we could count the rise over 1.
Okay, we can count rise over run. So if we're starting at the first point and we're rising to be even with the second point, how far up do we have to go? It might be easier if you look at the numbers in the table. The first one is 032. The second point is 541. So how far up do we have to go? 9. And then we go to the right. There's our run. 5. So our slope is 9/5. The rise is 9. The run is 5. And B is, what did we say B was?
32.
32. And what's its significance on the graph?
When the Celsius is 0, the Fahrenheit is 32.
And specifically in the graph, it's the y-axis, where the graph crosses the y-axis. Okay, so again, the slope is 9/5. Rise is 9. And run is 5. B is 32, and its significance is that's where the graph crosses the y-axis. Number 4. Write an equation describing the relationship between Celsius and Fahrenheit temperatures. You can use a table, the graph, or methods learned earlier in the cycle. So we're writing a formula, or writing the equation. It's really going to be in the form of y equals mx plus b. But instead of y, what are we going to use for y?
F.
The Fahrenheit is equal to, what slope do we have? 9/5. X is
C
C
plus 32, right?
plus 32, yes. So notice that this is a formula for F, or Fahrenheit. Any questions so far? Number 5. Identify the M and B using the equation in number 4. Well, this seems kind of silly. Going back to the equation number 4 we just found, what was M? 9/5, and B was? Okay, B. Explain how you know the formula for F is a function and why this is important.
For every y input there, or for every x input, there's a y.
Okay. Let's use the C's and the F's in this case. So for every C value we substitute in, we get exactly one F value. On to number 6. How can the linear model be used to find the Celsius temperature that corresponds to 0 degrees Fahrenheit? Do the calculations and state your result. So we have our linear model at the top of the page. F is equal to 9/5 C plus 32. So how can we use that to find the Celsius temperature that corresponds to 0 degrees Fahrenheit?
You put 0 in for that.
Very good. Just put 0 in for the F. And now we have to work that out. What's our first step going to be?
Subtract 32.
Subtract 32. So negative 32 is equal to 9/5 C. We still have to get the C by itself. How do we get rid of that fraction?
Multiply by its reciprocal.
Good. Multiply by its reciprocal, which would be 5/9. We do that to both sides. So on the right side, those 9's cancel out, so do the 5's, and we're left with C, which is exactly what we want. So that negative 32, you can put that over 1 if that helps you. Multiply straight across and then divide by 9. So we should end up with a negative answer. I believe if you multiply straight across, you get negative 160. Is that correct?
Yeah.
Over 9. And divide it out. And they rounded to 2 decimal places. What would you get?
17.78.
Okay, but negative. negative 17.78 degrees Celsius. Any questions on A? Letter B. Imagine doing this 10 more times and converting each Fahrenheit temperature to Celsius this way. Would that be efficient? No, probably not. What could make the process faster? Any ideas on what could make the process faster?
Can you get rid of the 9/5 first or no?
Can you get rid of the 9/5? Kinda. There's more to it. Let's look at the equation that we have right now. F equals 9/5 C plus 32. It's much easier to substitute in a value for C and work it out than it is to substitute in a value of F and work it out. Do you agree with that? So what might make it easier if we solve that equation the one time for C and then substitute in. Then we'd have everything on one side like we have with the F. Okay, so what could make the process easier? Solve the formula for C. Bottom of page 457. Formulas allow us to find the value of one variable by evaluating the formula for a value of one or more other variables. When an equation is not solved explicitly for the variable of interest, as in number 6, we will need to solve an equation to get the value we desire. This can be tedious if we need to do so repeatedly. Instead, we could solve the equation once in the general case to get a new formula to use in specific cases. To solve the formula for C in the general case, we need to understand how we did so in the specific case. So number 7. List the steps in order that you used to solve the equation in 6a. So what did we do first in 6a?
Subtract.
We subtracted 32, and then what did we do?
Multiply by the reciprocal of 9/5.
We did, okay. So number 8, since we are trying to solve for C, treat C as the only unknown. Treat F in the equation as a number since it will eventually be replaced by a number. Using the steps you listed in number 7, solve for C. So we're going back to our original equation. F is equal to 9/5 C plus 32. So we're going to follow the same steps we listed in number 7 to solve this for C. So we subtract 32. So F minus 32 is equal to 9/5 C. The next step is to multiply by 5/9. So the right side, the 9's cancel and the 5's cancel, and we're left with C. And we have 5/9 times the quantity F minus 32. Any questions on number 8? You could have distributed the 5/9, but then it would get a little messy with the 32. Okay. How it works. To solve a formula for a specific variable, number 1, determine the variable that will be treated as the unknown. Number 2, treat all other variables as constants. Number 3, solve the equation for the unknown. For example, the formula I equals PRT is a formula for computing simple interest, I. If we want a formula for P, which is the principal, we need to solve for P. It becomes our unknown. Treat all the other letters as though they are numbers. Since P is multiplied by RT, undo that by dividing each side by RT. So that means you would end up with P being equal to I over RT. And now we have a new formula for P in terms of I, R, and T. Any questions on that example? Okay. Number 9, there's an A, a B, and a C. See if you can solve those for the different variables. So letter A is similar to the example in how it works. In this case, we're solving for T, so we want to get this T all by itself. That means we need to get rid of the R. How do we get rid of the R? Divide by R. And that leaves the T, which is equal to D over R. Any questions on A? Letter B. This time we want to solve for the little r, which is right there. So that means we'll have to get this term by itself. How do we get rid of the P?
No.
Which P?
Yeah.
Well, I just said that we want to keep this term, or we'll have to get this term by itself. So this is the P, the first P that we have to get rid of. We need to subtract it. So A minus P is equal to PRT. Now we still want to get that little r by itself. What do you think we should do next? How do we get rid of the big P and the little t?
I divided by P, and then I divided by T.
You can actually divide at the same time. So you can divide by PT. Then the P's cancel, and so do the T's on the right side. And we're left with the little r, which is exactly what we want. So we have A minus P over PT. Any questions on letter B? Letter C. We want to solve for r. So first we'll have to get the r squared by itself. How do we do that?
I divided by 4.
Okay, let's divide by 4 pi. So that cancels the 4, that cancels the pi. So now we have r squared is equal to s over 4 pi. But we want this to equal r. How do we get rid of the square?
We take the square root of
Exactly. The square root of both sides. The square root and the square will cancel each other out. So that leaves you with r is equal to the square root of s over 4 pi. Any questions on letter C? Okay, number 10. Find the slope and y-intercept of 4x minus 3y is equal to 12 by writing the equation in slope-intercept form. So what does the slope-intercept form look like? What What is the slope-intercept for?
It's y equals mx plus b.
Y equals mx plus b. So that's telling us we need to take that equation they gave us. We have to get the y by itself. So how do we start?
You add it to get the wait.
I'm sorry?
Can you? No, you can't. You can't add the 3y, can you?
You could, but there's probably a better way to go.
Subtract the 4x.
Let's subtract the 4x. So negative 3y is equal to negative 4x plus 12. What else do we need to do to get the y by itself?
Divide by 3. Negative 3.
Yes, very good. Divide by negative 3. We want to get rid of the sign as well as the number. So we divide everything by negative 3. So these negative 3's cancel out. And y is equal to, what's negative 4 over negative 3? We can simplify that fraction a little bit. What can we do?
Change it.
How could we simplify negative 4 over negative 3?
It's a positive.
It becomes positive. A negative divided by a negative is positive. So 4/3 x. What about 12 over negative 3?
Negative 4.
Is negative 4. So we can just write that as minus 4. And there it is. Any questions on number 10? Number 11. Write your formula for C from number 8. Below it, write it again, but after having used the distributive property. Both formulas should use fractions, not decimals. So the original one, we had C is equal to 5/9 times F minus 32. Now they want us to distribute that 5/9. So C is equal to 5/9 F minus what?
Negative 160 over 9.
There you go, 160 over 9. The 5 times 32 is 160, and 9 times 1 is 9. Questions on part A? Part B says to evaluate each formula at F equals 212. So if we substitute the 212 into the first equation, we would have C is equal to 5/9 times 212 minus 32. So what do we do with that?
And subtract
Let's start in the parentheses. So subtract 212 minus 32 is, sorry?
180.
180, which works out very nicely because 9 will go into 180. So we can reduce. We can cancel the 9, and 180 would become 20. And 5 times 20 is 100 degrees Celsius. And now they want us to do the same thing, but use the other formula. So C is equal to 5/9 times 212 minus 160 over 9. So notice we do have a common denominator of 9. So even if we could reduce the 9 and the 212, we probably don't want to do that because we're going to have to subtract anyway. We'll need a common denominator. So in that first part, let's just multiply straight across. What is 5 times 212? 5 times 212.
1060.
1060 over 9 minus 160 over 9. So now we can subtract those numerators. What'd you get?
900 over 9.
900 over 9, which does work nicely. That's also 100 degrees Celsius. Do you have any questions on part B? Part C, which was easier to use and why?
The first one.
First one was easier. Why was it easier?
So you didn't have to deal with fractions very
So we only had to deal with the fractions once at the end. Okay, continuing on page 459. The right side of the original formula in number 11 is written as a product, while the right side of the second version is written as a difference. Since the pieces that form a product are called factors, quantities that are written as products are said to be in factored form. So our original one is said to be in factored form. So factoring is the process of writing a sum or difference as a product. For example, the expression 3x plus 6 is not factored since it is a sum of two terms. However, 3 times x plus 2 is an equivalent expression, but in factored form since it is a product of the quantities 3 and x plus 2. Any questions on the box? One type of factoring involves the greatest common factor, or GCF. Factoring using the greatest common factor is the reverse process of the distributive property. Let's look more closely at this type of factoring. Page 460, example 1. Under each term on the right side of this formula, list the factors. So looking at the first term, what are the factors? Not 2. 1/2 would be one of them. What else in the first term? H and also B1. Those are all multiplied together. Those are all factors. Now look at the second term. What are the factors there?
1/2 H and B2.
There you go. 1/2 H and B2. Now the next part says to list the factors that appear in both lists. In other words, the factors the terms have in common.
1/2 in the H
1/2 in the H.
and well, would B be common or
No, they would not, because they're different. Because one has a subscript of 1 and the other has a subscript of 2. So they are not the same. Now the next part says write the product of the common factors in front of the parentheses. So the area is equal to 1/2 H times something. So far so good? Complete the parentheses with two terms as we started with, so that the expression was simplified using the distributive property of multiplication. It would look like the original expression. So in other words, if we wanted to end up with our original, what do we need to multiply the 1/2 h by to get that first term back up there?
B subscript 1 plus B subscript
Okay, yeah.
2.
B subscript 1 to get the first term, and you're right, we would need B subscript 2 to get the second term. If we distribute the 1/2 h, we'll get what we started with. So they are equivalent, but this last one is in factored form. And you can check your work by distributing. So if we distribute here, we would have 1/2 h b1, and then distribute to the second term, we would have 1/2 h b2, exactly what we started with. So our answer is yes. Any questions on example 1? Example 2. Well, they want us to first of all list the simplest factors of each term. I think we're going to skip that line. And then it says list the factors that appear in both lists. In other words, the factors the terms have in common. We're going to skip that. We're going to go right down to the next part where it says write the product of the common factors in front of the parentheses. So let's go back to our original. Look at the numbers first, the 3 and the 6. What could you factor out of both of those?
3.
A 3. Now let's look at the x's. We have x squared and we have x cubed. What could we take out of both? X squared. You want to take, first of all, that variable has to appear in both, and then you use the one with the smallest exponent. So x squared is what they have in common. What about the y's? Right, there's just one, and it's only in one of the terms, so we cannot factor out a y. It does not appear in both terms. Whatever we take out, we have to be able to take it out of both. So now we want to distribute and get what we started with. What do we need to multiply 3x squared by to get 3x squared? 1. What do we need to multiply 3x squared by to get that second term? Well, we need a -2, and I'm sorry, what'd you say for the rest of it? X. Yep, we need an x to get x cubed, and we also need a y. We already completed the parentheses with the two terms. Notice that we started with two terms, so we will need two terms in the parentheses. They want us to check our work by distributing. So if we distribute to the first term, we would get 3x squared, and then the 3x squared times the second term. A positive times a negative is negative. 3 times 2 is 6. X squared times x is x cubed, and then we also have the y. So do we get the original equation? Yes. It says generalize which factors go in front of the parentheses so we can factor the greatest common factor more quickly. Well, that's actually what we did. We looked at what they had in common and we brought that out. So that's all that means. Let's look at the how it works box, page 461. To factor the greatest common factor of the terms, or find the greatest common factor of the terms. This will be the product of the GCF of the coefficients and the variables common to each term raised to the lowest exponent that appears on each variable. Number 2, write the GCF in front of a set of parentheses. Number 3, fill the parentheses by determining the terms necessary to create the original expression if the distributive property with multiplication was used. So note, number 1, the number of terms in the original expression will be the number of terms in the parentheses. Number 2, If the terms do not have any common factors other than 1, the expression cannot be factored using the GCF. So for example, suppose we want to factor this expression by using the GCF. The GCF of the coefficients is 7, since 7 is the largest factor of 14, 28, and 7. So far, so good? Okay. Notice that W and Z are the variables common to all terms. The lowest exponent on the W among all of the terms is 1. This is also true for Z. So the greatest common factor is 7WZ. We write this in front of a set of parentheses and fill them with the 3 terms that would get us back to the original expression if we use the distributive property. So factored form would be 7YZ out in front, and then in parentheses 2x minus 4z squared plus 1. Any questions on that? Okay. Practice. It says factor the right side of the formula using the GCF in 2 different ways. Once by taking out the positive version of the GCF, and a second time by taking out the opposite of the GCF. Okay, so our greatest common factor. What about the number? What can we factor out of everything?
2.
Any x's? X squared. Any y's? No, we do not have y's in every term, so we can't factor out any y's. So what would we have to multiply 2x squared by to get that first term back?
3, negative 3. Wait. First term back?
To
1.
get,
Yeah.
we need a 1,
Negative 1.
negative 1, or you could just say negative, because we'd also need an x. If we did not need an x, we would put in the 1. And you can put in the 1 if you want to. You don't have to. So that would get us the first term back. We would get negative 2x cubed if we multiplied those. What do we need to get the middle term back? First of all, plus or minus?
Plus.
Plus.
4.
Not 4. Remember, you're multiplying.
3.
2 times 3 would get us a 6.
X.
Did you say x?
Yeah.
Yes, we do it in x. X squared times x will get us the x cubed back.
Plus y.
And we also need a y, but don't put a plus in there. Now, how do we get the last term? First of all, do we need a plus or a minus?
Minus.
Minus
6. 6.
That'll get us the negative 12. And we already have x squared. So that's it. Any questions on factoring the first one? So now they want us to do the same thing, but instead of taking out 2x squared, they want us to take out a negative 2x squared. They want us to take out the opposite. So compare that with what we started with. What would we need to multiply by to get the negative 2x cubed back?
X.
And x. Now go to the second term. First of all, do we need a plus or a minus?
Minus.
Because a negative times a negative will get us the positive in the middle. What else?
3. X. Y.
Very good. The last term, first of all, do we need a plus or a minus?
Plus.
A plus. Negative times a positive will give us the negative. What else do we need?
6.
6. And we already have x squared, so that's it. Which one did you like better? First or second?
Pretty much the same.
Pretty much the same? Okay. which is true. However, in factoring, many times factoring out a common factor is just the first step. And if you would have to factor again, then this method, the second one, would be better because it's easier to factor inside the parentheses there if that first term is positive. So that would be the only difference. If you had to factor again, it's better than the second method. Okay, bottom of page 461. Factoring the greatest common factor takes a common element from a set of terms and lists the elements once instead of in each term. This process is useful in mathematics, as seen in the next example, but also in real life. When two people share a last name, like Will Smith and Ella Smith, it is easier and faster to use Will and Ella Smith. Okay, so we are almost done with section 9, but we will stop there so we have time for the quiz. On Monday, we will finish section 9, and then we will do some factoring that's not in the book. So I'll bring some worksheets along that we'll work on.